Projectiles, inclined plane, type 4 landing angle. So here in 1993 we have a particle is projected up an inclined plane. So it's important to remember that we're going up the plane. The line of projection makes an angle of 30 degrees with the plane, and the plane itself is inclined then at 30 degrees to the horizontal. And again, we're always told the plane of projection is vertical and contains the line of greatest slope. So again, it's not veering off to the left or the right, it's going straight up. And the first thing we have to do then is express the velocity and displacement of the particle after t seconds. And we have to do that in terms of I and j. And then we have to calculate theta itself, where theta is the angle that it strikes the plane at. So we want to draw our diagram first so we can see what is happening. So we have our horizontal ground, and the plane is at an angle of 30 degrees to the horizontal. We have the particle is projected up the plane at a velocity of u, so an initial speed of u, and that projection is making an angle of 30 degrees with respect to the plane itself. So as it's projected up the plane on landing, our angle we tend to call L, and we know that on landing Sy is equal to 0. And of course then that our landing angle is equal to minus Vy over Vx, because of course if I resolve this velocity vector, I can see that my Vy is in the opposite direction to the initial velocity, which is going up, and it's in the same direction in the x direction. So remember, whenever you're resolving your vectors, always use a different colour or broken dotted lines to distinguish between them. You can't have three solid lines representing a vector and its resolved vectors and its resolved components. Okay, so what information do we know? Well, we have our alpha and our beta. So I'm going to mark that as alpha and that's beta. They're both the same angle. So of course, if I'm looking at alpha being 30, then sine alpha will be sine 30, which is a half. Cos alpha will be cos 30, which is root 3 over 2. If beta is equal to 30, we're going to get the same answers for sine beta and for cos beta. Okay, so what I'm going to get you to do now is you're going to make out your table for me. So you're going to pause the video and you're going to do U, A, V, S and T in terms of X and Y. So remembering that U is equal to U cos alpha in the I direction and U sine alpha in the J direction, we're going to fill out our tables based on this. So we have U cos alpha. Well, cos alpha is root 3 over 2. So therefore that's going to be root 3u over 2. And in the y direction, it's u sine alpha. And of course, sine alpha is a half. So therefore that's going to be u over 2. A, our gravity, remembering from our previous videos that if we're looking at resolving our gravity, we have minus g sine beta in the x direction. And sine beta is a half. And we have minus g cos beta, which is minus root 3u over 2 in the y direction. So therefore v is equal to u plus at. So if we get vx, that's going to be u plus at. And v in the y direction is u plus at. S in the x direction is ut plus a half at squared. And S in the y direction is ut plus a half at squared. And then we have t is obviously going to be our time. Okay, so the first thing it wants here now is, it doesn't normally ask for this, but we're looking for our velocity and displacement in terms of I and j. So therefore for part 1, if we're looking for our velocity vector, well, that's going to be Vx, which is our I direction, in Vy, which is our j direction. So our Vx and our Vy then, if I sub in, well, what did we say Vx was? We said it was root 3u over 2. And it was minus g over 2t. So that's in the I direction. Plus in the j direction then, it's u over 2 minus root 3. Sorry, that should be a g there. Just see that mistake there. Sorry about that. So that's minus root 3g over 2. So we have u over 2 minus root 3g over 2 times t, and that's in our j direction. And if we go back to the question, it's looking for velocity, not speed. If it said speed, then we would have to get our magnitude. In other words, we'd have to get the square root of a squared plus b squared. But it says velocity vector, okay, in terms of I and j. So the next one it wants then is, again, displacement. So again, it's looking for displacement and not distance. So again, it's going to be our s in our x direction, which would be our I component, and s in the y direction, which is our j component. And again, we don't need to get the magnitude, we just need to write it in terms of I and j. So therefore our displacement vector is going to be root 3u over 2 times t in the I direction. Sorry, no, go back. Root 3 over 2 plus g over 4. Definitely one of those days. That should be a minus there as well. Sorry. Okay, minus. Grand. So we have root 3u t over 2 minus g t squared over 4. And that's in the I direction. And then we have plus ut over 2 minus root 3, and there's my g again, root 3g over 4t squared. And that's in the j direction. So that's the first part of our question done. Okay, so the second part then says to calculate theta. So as normal, we say on landing, we know that sy is equal to 0, and this is going to be allowing us to find our time of flight. So our sy is our ut over 2 minus root 3g over 4t squared. So if I let that equal to 0, and then I multiply across by 4, because it's my lowest common denominator, I'll end up with 2ut minus root 3g t squared equals 0. Highest common factor is t, leaving me with 2u minus root 3gt. Both of these multiply to give us 0, which means one must equal 0, or the other must equal 0, or both must equal 0. So getting t on its own then gives me 2u divided by root 3g. And this is my time of flight, because t will equal 0 at the start. In other words, the particle is sitting on the plane, it's projected from the plane. Okay, so now what I need to do is work out the tan of my landing angle. So tan of my landing angle I know is equal to minus Vy over Vx on landing, and on landing at the time of flight. So again, you can work out your Vy and your Vx separately, or you can set them all in one go. I'm going to do it out separately for you there. So we have u over 2, and if I go back, we can see that Vy was u over 2 minus root 3g over 2 times t, where t is our time of flight, 2u over root 3g. So that gives me u over 2 minus root 3g over 2 times our time of flight, which is 2u over root 3g. That's nice, because root 3 goes into root 3 once, g goes into g once, 2 goes into 2 once. And that leaves me with Vy is equal to u over 2 minus u. So Vy is equal to minus u over 2. So as we expected, our velocity in the y direction is negative because it's in the opposite direction to which the initial velocity was for the y direction. So now we want to do our Vx, and again our Vx, if we go back to our table, is root 3u over 2 minus g over 2 times our time of flight, where our time of flight is 2u over root 3g. So we have root 3 over u2 minus g over 2 times 2u over root 3g. So g will go into g once, 2 goes into 2 once, and that leaves us then with root 3u over 2 minus u over root 3. And then if I add those two together, lowest common denominator there is 2 root 3. Well, that gives me u over 2 root 3. So therefore we can say that the tan of our landing angle is equal to minus Vy, so that's going to be minus u over 2, so u over 2, divided by u over 2 root 3. And of course, if I'm dividing by a fraction, I can turn it upside down and multiply. And therefore, u goes into u once, 2 goes into 2 once. And what are we left with? Well, we're left with tan of the landing angle is equal to root 3. But it doesn't want tan of the landing angle this time. It wants the angle itself, theta. So the landing angle, which was referred to as theta in the question, is equal to tan inverse of root 3. So, of course, we can go to page 13 in our maths tables, or, of course, using your calculator. But if you're using your calculator, please beware. Make sure that your calculator is in degrees there. And if I get tan inverse of root 3, well, what do we get? Well, we get 60 degrees, of course. Okay, so nice question that.